Welcome back. Our next learning module is on this topic of user-defined functions in C. And certainly we've been using functions ourselves all semester long for the various programming practices and projects that you've been working on. And this topic is really more about making sure we have a clear understanding of how we define our own functions for future use in our own programs or potentially for other people to use in their programs. Conceptually, I think we understand that, but just to make sure we're all on the same page here, in C, when we call something a function, it's just a way of modularizing your program, allowing you to break down functionality into individual, potentially reusable blocks of code. There's a syntax for declaring our function that we will see, and then what we've been using all semester long is this usage syntax, where for a function of a given function name of various different input arguments and a potentially a different return type for a variable, we actually would then use the name of that function and then in parentheses provide inputs to that function for those arguments, as well as potentially optionally being used for creating a variable for an assignment expression purpose. And I ask here, we've seen these before. Well, we've seen these all semester, right? We've been using functions all semester long. Couple just little caveats here that we'll see, and we have seen that not all functions actually have to have a return value, and actually also not all functions have to have input arguments as well. Many of the interesting functions we would want to use would have input arguments, but it's actually not a requirement that we do have those input arguments. By default, and for every program that we've written so far, every C program is required to have at least one function, and that function is going to be generally called main. It has an input that we saw, an optional input, which is a set of character strings provided as input to the execution environment. We briefly touched upon this in LM-06, but in our Replit automated testing environment, we really can't use that feature well, so we're not using it for any of our programs. And then there's the output, which is an integer to define, to represent the exit status of the program. For almost all of our programs, we've just been returning 0, having return 0 being the end result of our main function. And because main is assumed to be there in every one of our C programs, we don't actually have to have a function prototype. So that is our basic int main with actually no input argument there, returning 0 at some point in it. And we've been using many different functions, right? But the most consistent 3 we've been using is that scanf to read in text from the user, printf to print out messages to the user, and then that ran function to optionally generate a pseudo-random integer number in that 0 to rand max range there. That's all part of that C standard library. And if there's been one takeaway so far this semester that I want you to really have a good handle on is that understanding that things that are there for you in the standard C library are there to make your life easier as a programmer. And the kind of tasks that maybe otherwise would take you quite a bit of code and quite a bit of struggle to get working can be much more simplified by using existing provided library functions from the C standard library. So we know a whole bunch. Basically every week or every learning module, we've been learning more as we've going, and they're there for you to make your life easier. Sometimes there's a little bit of an upfront cost of having to read that documentation, but once you've understood how to correctly use those functions, they do make your life a lot simpler at the end of the day. So here is our first function. Of course, we've been using functions. Here is our first quote-unquote user-defined function, which would, in theory, calculate a simple multiply-accumulate operation that given input variables, calling them maybe variable 1, variable 2, variable 3, or in the function itself, m, x, and a, it calculates the value of m times x plus a. So we have our we have it from top down here. We have our main function here where we declare some local variables to both provide as inputs to that function call as well as a fourth variable to actually store the result of that function call. And then elsewhere in the code, we have our myMac function here that declares its 3 different inputs, float m, x, and a. And then although we don't strictly need to define a separate temporary variable here, we declare one to first store the result of m times x. We then add to that the result of a. That's what calculates m times x plus a. And then we finally return that temp variable here. Let's take a look at that function in action here. So it's the same exact code. The only difference in this version versus the version on the slide is at some point we had to initialize those variables to something to get that program to work. So other than that, that's exact same code that we have here. So we hit our magic run button, and what happens? Well, we may have already gotten a hint that something might have been the matter, and we could have looked at our IDE here to see implicit declaration of function myMac is invalid in C99. That's not super duper useful, but basically what it's saying here, and something has gone wrong, is that when we have declared our function here, the compiler is following the rules of the language. It's just another piece of software itself. And most compilers, and certainly part of the C standard here, is that it doesn't know at compile time what that function, the meaning of that function my underscore mac is, if it hadn't seen it before. And there are two ways to resolve this problem. I'm not necessarily saying one is necessarily better than the other, but one's much more common than the other. Is to first, one solution is to define that myMac function first, so that by the time the compiler reaches function main, it'll actually know that that function existed. Oh, I see this call to myMac. I previously saw a myMac function. That must be the one that the programmer is referring to. That is a valid solution. It technically works. But then you really have to worry about the order in which in your code your functions are found. And we don't usually lay out our code based on that organizational principle. More likely it's based on just functionality as we're building up. So that may be the exact opposite order we would normally be writing our functions here. The other approach is to use this so-called function prototype to sort of pre-declare what functions are going to be in your program before you actually use those functions. We can show both solutions because they both do technically work here. The first potential solution is, well, if we know we're calling this myMac function earlier in the code, the solution is just to define that function earlier. So here, if you saw what I did, it was a quick kind of cut and paste. myMac didn't exist or wasn't aware of myMac beforehand. It now is aware of it because it sees it first. You can see the red squiggles are gone, and then the function actually does compile and run. It doesn't print out anything, so that's not terribly interesting. So that is one solution here. And the other solution, even in the more, I would say, common recommended case in which the ordering is kind of irrelevant or main comes before the caller function here, is to instead declare that function prototype. And that syntactically, as we'll see on the slide here, looks very similar to the actual function itself, or that header, that first line of that function. But instead of using the curly braces to denote here's where the innards of that function are located, it's just the actual input and output and name of that function with just a single semicolon here. This line 4 of our program now doesn't do anything in and of itself. It's really there to let the compiler be aware of, hey, there's this function that will exist somewhere in your program. It's going to look like this. Look out for it. When someone's calling it later on, it's going to be okay because that function should exist. And while we don't really peer into all the guts of these .h files we've been including all semester long, that's what they have in them. They have other things as well, but that's the primary purpose of that .h, that header file, is to say in the standard I/O part of the standard C library, here are all the functions that exist. Function name, inputs, semicolon, so that when you call them, compiler is aware that they will exist. There's a separate step where ultimately the linker has to find those, and we're not dealing a lot with linker issues this semester, but at least in terms of using standard C library functions or using your own user-defined functions, having that function prototype is a pretty good solution. And that's all that it's really saying here on this slide. So that prototype is here to provide that hint to the compiler regarding any predefined functions that could be in use, and the syntax is very similar to when we're actually declaring the function. Float myMac, float, is a hint to the compiler saying, in my code, there is this myMac function with these inputs and this output. So as I mentioned, you either put those in the beginning of your C program you're compiling, or you create your own separate header file and put them there. If it's one function, two functions, it's debatable whether there's much value in having your own separate .h file to include those, but that is an appropriate approach to building these functions. That's more of a style debate versus a hard and fast rule, but then that would be the suggestion here, that in our files we have for main.c, we would also create like a main.h. Not that common to call it that. Usually your header file would have something to do with some other functionality other than just the program itself, but inside that main.h we could then declare that function, and then we would include that. Whether it'll work with the double quotes or versus the brackets here, this should still compile and work. And if you saw on that slide, the other thing that was debatably interesting is, for our function prototype, you actually don't need to name your variables because you're not using the variables in this code. So this syntactically is equally as good, saying I have a return value of float and I have 3 input floats. And in fact, I don't care what the names are at this point because I just need to know that there are 3 of them. When I finally then go ahead and provide the implementation for that function, well, then I certainly do care about the names for those variables as our inputs at that point. So, and the order does then matter, that the first one would correspond to M, the second one would correspond to X, the third one would correspond to A. But you don't strictly need to have the M, X, and A right here. I think it's fine to still have them, right? It should be kind of a copy-paste operation. And in fact, that's what we did, right? We copy-pasted that first line of the function itself to the function prototype. You're going to do that quite often. You'll recognize that you need a new function. You'll write the prototype for it first very commonly, and you'll copy paste that prototype as the first line of the implementation for it, just changing that semicolon to a set of curly brackets, and then there's your implementation here. That's going to be a pretty common approach I think you'll take as you're building your own functions. So I think we got this, right? These are the 3 main parts of the function. There's the prototype. You can think of this as the definition for the inputs and outputs, the black box, the interface for this. We can declare the names of the variables, but we don't strictly need to. So that's the black box for my Mac. 3 inputs, 1 output, all of type float for this example. There's then the actual implementation, right? The C code that's doing the actual work of the control flow, the looping, the arithmetic required to get a valid result for that function once it is called. Those input names will then correspond to the variables that are valid inside the function body. Then the third part is the actual usage, the actual calling of that function. And the terminology we use is there's a caller function and a callee function. The caller calls the callee. I don't know how important that verbiage is at this point in your kind of programming career development, but that is the terminology we use. So the caller calls the callee using its own local variables in place of the named inputs in the callee function. So there's those 3 parts that are required: prototype, actual implementation, and then the actual usage of it. So some other function, main in the example we had, is going to call that myMac, and it's going to provide values both for the inputs, its own local variables in the caller function will then get kind of copied into the input variables for the callee function, and then optionally, and as often will be the case, a local variable to store the result, the return result of that function here, providing valid inputs that function is expecting. So when do you need to make a function? I guess in this class, the answer is really easy. It's when I tell you to. You'll have Learning Module 9 programming practices, and I'll say, write this function, and then you're expected to write that function. Okay, that's a short answer for now. Another good rule of thumb is that there's some non-trivial functionality that you are working on, and you think you may use it again, in the future, right? I'm writing this code. It's pretty complicated. I'm doing some sort of algorithm or doing some sort of interesting thing with my input variables here, and I could see myself using this in the future, either for yourself. That's still a valid reason to create a function, or you're going to create your own library for other people to use. And another potentially good rule of thumb, and it is really just a rule of thumb, is you're writing all this code and it's inside this function and it's just becoming all these lines of code here. If there was a way to cleanly kind of separate some core piece of functionality out there, that may be very useful then to make that its own function. But that's just sort of a heuristic versus like a hard and fast rule. So for this class, you don't have to answer that question. You make a function when I tell you to make your own function. But in general, that's something you have to kind of work on. Understanding when will code reuse be useful, that's point 2 here, or when is just kind of code simplification potentially useful, that's point 3 here. But there's no like guaranteed answer, for when you should make your own function otherwise. In terms of what this means from a memory perspective, you may often hear this term, like, we'll put this on the stack, or this thing is put on the stack. This is a specific data structure that allows memory to manage where things are going to be put when you are doing that caller to callee transfer of control flow in your program. It's really actually architecture specific. There's also software application binary interface standards that allow you that are there to specify how a caller function should be dealing with memory when it's doing a callee function. So there's that standard that allows for interoperability so that your compiler output could match what my compiler is expecting on the input side. But from an architecture perspective, it does tend to be really specific. So your M1 MacBook, which is ARM based, will have a much different ABI than my laptop that is an Intel based microprocessor in it. I think for our purposes, this is sufficient to just be aware that there's this concept of a stack. Later on in your academic careers, you'll learn a lot more about both architecture as well as memory management and what this means from a function call perspective. But this high level view, I think, is sufficient. So caller function is calling the callee function. There's going to be some data that gets placed in memory in this stack type of data structure to keep track of where things are. The ABI and the compiler are taking care of that code for you, but being aware that that code exists, that there's actual overhead both in memory space and an execution time of calling a function is important to be aware of. And we covered scope before, but I want to talk about some of the workarounds for kind of the existing scope rules. We talked about scope of variables and how we can declare our integer inside our for loop, and that integer is only going to be valid inside that for loop. And when we talked about that, I mentioned, use that with care. For int I equals 0, that makes reasonable sense, but don't just be declaring local variables just for the sake of doing so. But this awareness of variable scope from a function to function perspective is pretty critical. So when we do that calling of the function, there's that transfer of control flow. So my function main is it going to do some work, then call printf, then do some work and call scanf, and then do some work and maybe call myMac at that point. The control is going to leave in terms of which instruction is going to be executed next from this line, whatever line that corresponds to in assembly code in our architecture, to whatever that first line is of that program, or of that function, printf or scanf or myMac. Each function is going to have its locally defined variables with its own local scope, and so those variables are only going to be valid for those curly braces in which it's defined. That's the same rule as before. We just have to recognize that when we call a function, that function is not going to, at least by default, be aware of any of the variables we have in the caller function. They're in a different scope. So I declare int I in my function main, and then I call myMac. MyMac, unless we have some workaround, is not going to at all be aware of that integer I. You'll get the same kind of compiler error if we were messing around with scope like we were doing, earlier on in the course. So consequently, when you modify that input variable, which we didn't do in the example program, but if we wanted to modify m, modify x, or modify a in that myMac function, it will actually not affect at all the variable that we were using, var1, var2, var3, in our caller function. I'll show you some examples of that working, but just to go back to our code here, what I'm saying is we have these variables in the caller function, and they are of a certain scope. And then we have these variables in our callee function, those are all of a certain scope, including the input variables, m, x, and a. Those variables, both whatever temp or other things we declare, as well as the actual input variables themselves, have that scope of being valid only inside the function. You can change them. You can add something to them, set them to 0, do whatever you want with them, but that change only affects that scope inside the function. Another way to think about that is when we do that var1, var2, var3, there is an explicit copy operation that's happening underneath the hood here that copies var1 to m, copies var2 to x, and copies var3 to a. And because of that copy operation, if I were to set a to 0 for whatever reason inside this function, it would not affect var3 at all, at least by default. That is the issue with scope, and that's what we have to be aware of with regards to that scope of our functions called. And likewise, by changing a, we don't modify var3. Similarly, a does not exist at all once we've finished that function call. So the caller function is not aware of a at all. It cannot access a. It cannot modify that variable a. It is local to it. We sometimes don't want to have this be the case. We sometimes would like to have our variables inside a function to have more than just that local scope. So We do sometimes have, for example, a variable that has a global or a program that has some global state that we want the function to update. Now, I call these workarounds and to use them with care. It's really not a programming issue in and of itself, but it may be a sign that you're not necessarily breaking down the problem very well if you're using some of these workarounds. Now I use these workarounds. There's all sorts of reasons to have, for example, in this case, global variables in your programs. So they're not invalid, they're not wrong. It's not a sign you're a bad programmer if you have a global variable in here. But it can be very hard to debug when something is changing your variables outside of the functions that they're being otherwise used in. It looks like kind of a side effect. You've called a function, and this other variable got updated that had nothing to do, at least based on input and output to that function. That could be a pretty hard thing to debug when it's not working well. So I guess I would say use with care, and I do mean that. Use these workarounds, including the global variables, with care. Um, but it's not an uncommon practice to have, a single global variable, like a singleton it's referred to, that holds all the state about your program at a given time. We just have to be aware that that's the case. So there's a keyword to declare a variable as potentially being global. Or excuse me, there is no keyword to declare a variable as being global in C. So instead, what we just do is we define the scope of that variable to be outside any of our functions. So let me make sure, because I said it wrong at first and then correct myself. There is no global keyword in the language itself. If I type global int, that's going to be an error, a compile error, and it showed it as an error. But with our scoping rules, in which a variable is valid inside the curly braces in which it's defined, if then in fact we declare this variable outside of any curly braces, outside of main, outside of any update or other function here, then in fact it would have global scope. And any function in your program would be able to potentially access it. This can get tricky as you have multiple files and things like that. There is a keyword to define something as an externally declared variable, meaning there is a global variable, but it's not defined in this program, in this code that I'm working on. For working on everything in one file, at least, just declaring it outside of your functions is going to be sufficient. Let's take a look at this code real quickly here. So we have integer a is 1, b is 2, c is 3. We call this update function 3 times and print out the result of the update function. And this update function is taking the variable and multiplying it by that global. And then it is also incrementing that global variable. So global is 3, we multiply a times 3, and then we change global to 4. Then we multiply b times 4 and return that result. Then we increment it to 5. Then we take that value of 5, multiply it by c, which is 3. And we do actually see the results as expected with global scope here. We've declared our variable outside of any function, and consequently, this myGlobal++ actually works as intended. The results were 3, 8, and 5. Remember that briefly here. If instead we had declared that global function local in scope, just because it's called myGlobal doesn't mean anything, and we initialize it to 3, and then we do that multiplication and then increment, I told you can change those variables, but the scope of those variables is limited to that function call itself. So instead of 3, 8, 15, the result is just going to be 3, 6, and 9. Global gets incremented, but then it gets reset again the next time you call that function. So that's the main difference between those two versions of the code. Our workaround is declaring this global outside of the function itself, such that when the function update increments myGlobal, that value actually does get changed from 3 to 4 to 5. You can do whatever you want with it, and any function can do whatever it wants with that myGlobal variable. Another workaround, which we'll have to talk about how to do this properly relatively soon here, is to pass the variable as a pointer to the function. And we've done this with scanf, so we've been doing that all semester. But by sending the pointer, the actual memory address of the variable to the function, we can actually update the variable's value in the caller function by updating the location in memory of that variable versus just updating the variable name itself, which would be local scope. So this example here, we have, again, int main with 3 local variables a, b, and c. We have a function called doubler, which is just going to double the values of those variables. And let's take a look at it here in our Replit environment. This example is called function pointers. Probably a slightly better name would be functions with pointers and not function pointers, but that's fine here. Functions using pointers, because a function pointer is something different, as we will see here, but in the next learning module. But we have our local variables, 2.0, 3.0, 4.0. Excuse me, we have our local variables a equals 1, b equals 2, c equals 3. We call this doubler function. We don't pass the values of a, b, and c. We pass the addresses of a, b, and c. We've been doing that all semester with scanf for effectively the same reason. That is a workaround of this limitation of scope rules. When we call scanf, we want to update one or potentially many variables with that scanf call. We're passing the address of those variables to scanf. That's exactly what's happening here. But now syntactically, we see what that function would have to look like in terms of its interface. That instead of being passed 3 int values, we're actually being passed 3 int pointer variables here. And those pointers are then what are being updated in the function versus the actual ints themselves. We're going to talk more in the follow-on learning module about how to deal with pointers properly. We provide the address of a variable and create a pointer to that variable using that ampersand operator. We declare a local pointer variable using that asterisk or star operator here, and we want to then reference the variable. We use that star operator again to actually get the result that we're interested in here. So this function does work. When we run it, a is 1, 2, 3, the result is 2, 4, 6. We're actually following the pointer, taking the result of following that pointer, that's now a local variable, adding it to itself, and then updating that location in memory with the result of that computation. It's perfectly okay if that code doesn't make a ton of sense to you yet. You're not expected to use pointers yet, but that is our other workaround, and that's what scanf's been doing for us all semester long here. Sometimes, and this is definitely, I would say, a less invalid approach, we may want the function to actually remember the value of a function's variable in between calls to that function. From an implementation perspective, that is roughly the same as having a global variable, but from a code readability perspective, I would say it's a little bit different because we're declaring our intentions a lot more clearly here. And the keyword to do this is to declare the variable with the modifier static. So I declare a variable not as just an int a, but a static int a. And with that static declaration, as we compile our code, it effectively becomes a global variable in that it's initialized at compile time, and then as it's initialized, it doesn't change between our calls to that same function here. This example is kind of an overly clever random number generator. I don't think we have to walk through that example necessarily, but instead we have a more simple example of print static or function static here, where we have int a. We're not actually using it here. We're calling print static 5 different times here, and consequently, we declare a static int x, we print out the value of x, and we do x++. Now, if we didn't have this static keyword here, what would happen? Let's make sure you understand that before I hit the run button. If we didn't declare int x as a static, it would be the same exact value of x every single time. It would print x is now 0. We would increment x to 1, but then the function would be out of scope. We would start that function entirely over again. So our workaround, our additional workaround, is declared as static. Our other workarounds would have also worked for this case. We could have still declared this as a global, and we would get our incremented values. But again, as I mentioned, the downsides of doing that from a code readability and other perspective. Here we're being much more clear with our intentions of our code, that we do have this variable that will be initialized the first time that function gets called, and then it's going to keep its value in between functions call. You'll get the same result, 0, 1, 2, 3, and 4. You'll come up with some scenarios in where it may make sense for you to have static functions or static variables within our functions. They're not all that common, but there's certain use cases that make a lot of sense for having static variables there. And finally, the other approach that we will be using a decent amount, and we have used a little bit already, is understanding this relationship between arrays and pointers And by using that square bracket syntax to declare that one of the inputs is actually going to be an array, um, we actually can then pass that array as an input to our functions, and it actually works exactly the same as if it were a pointer being passed to that input. So in C, we always have to be careful with regards to the length of our arrays. So if it's a C string, as we talked about, and we have that 0 byte at the end, we don't necessarily have to pass the length to these functions. But for all other arrays in which we don't explicitly know the length of our array via something like a null byte, we should be passing that value to our functions here. And it's very similar from an implementation perspective to our pointers. The syntax is just a little different, but you get effectively the same result, which is you get to update the values of that array from within the function using that array syntax that we have. So here is our function, our program for functions using an arrays here. There's a little bit to walk through here. There's really just 2 examples here. Let's start with main for this. We declare an array of size 3. We're going to have a function called sum. And that function sum here takes as input the name of that array and then a length parameter as well. So looking at sum here, we're using that empty bracket syntax to specify that one of our functions is in fact an array, and our second input is to specify, here's how many elements one can expect for that array. If it's a C string, we usually don't need to provide it, but it's not. We need to know how long the valid input is for our array. We don't declare it otherwise. The function itself is not aware of the length of that array here, or it can be made in such a way that it's not aware of it. So this one is code that we've done 100 times now. We're looping through the array, we're accessing the individual elements of the array, and we're doing an accumulate operation here. We return the result of that sum. We're not actually then updating array in this particular function, but then this next function is actually an increment function. So we call it again with the variable name as one of the inputs, and then the length parameter. And this one is then updating the value of the array. And just like with using both our statics and our globals, we do actually get a result here where that array itself is being updated. It's 1.0, 2.0, and 3.4. We've added 1.0 to it, so we get 6.4 plus 3. We should get a value of sum after we've done that increment of 9.4. It was 6.4. We then called increment. We get 9.4. I'd like us to leave things here for right now. I want to talk about a special case of functions that I think are kind of fun and kind of interesting. This is probably enough to get you started with all the examples we have for the programming practice, but stay tuned for a separate video where we look at recursive functions and what that means both in theory as well as in practice.